For more information on tutoring, personalized video solutions, or how to support Moof University and the production of more videos, check out moofuniversity.com. Thank you and enjoy. Next up is ionization energy, and we'll start off with the definition. Ionization energy is the amount of energy, often listed in kilojoules, that is required to completely remove 1 mole of electrons from 1 mole of gaseous atoms or ions. Okay. So here we've got to have the sort of the reaction definition, right? The reaction that we actually see here. This is the reaction for the ionization energy. We start off with X, which is the elemental symbol of some atom, okay, some element. And it's initially neutral, at least in this case. And we're going to take off an electron. So we're going to have an electron freed up over here to the right. You see that. That electron is freed up. And what results is that this initially neutral atom in the gas form is now a gaseous ion. Specifically, it has a positive charge. So it is positively charged, which is actually pretty important to keep in mind. Now, the change in energy associated with this reaction is the actual ionization energy. Okay, and in this case, it's called ionization energy 1, known as the first ionization energy. Okay, so upon hearing that, you're probably thinking, okay, that must mean there's a second and third ionization energy, and we'll get to that shortly. Okay, now, the change in energy associated with this reaction, the ionization energy, is often measured in kilojoules per mole. It's a positive value. Always, okay? And we'll get to that in just a second, okay? So just as an example here, I want to show you, for instance, for sodium. If you start off with sodium in the gaseous form, we rip off an electron, and we get sodium plus, and we get that free electron. The energy associated with that is 500 kilojoules per mole. Okay, so that would be the ionization energy 1, the first ionization energy for sodium. Okay, now the question is, why is energy required to make this happen? Okay, we're talking about pulling an electron away from an atom's nucleus, which is positively charged, right? Electrons are negatively charged and are therefore attracted to the nucleus. The two, the electrons and the nucleus, do not want to be separated. So if you want to pull them apart, if you want to take an electron and pull it away from something it's attracted to, you're going to have an input of energy. And so that's why the ionization energy is always positive. So I should actually note that here. It's always positive. Okay. In fact, required kind of implies that. Okay. Now, another question is, can the ion that results from the ionization energy reaction have its electrons removed from it? Well, assuming it has electrons left to be pulled off, then yeah, that can happen. Okay. And how would that look? Well, if we have this X plus in the gas form and we rip off an electron, we'll lose another negative charge. So now we go from X plus to X2 plus. Okay. And that's still an ion, right? Now it's a more positively charged ion. Now, the change in energy associated with this, right, the energy required to make this happen is called the ionization energy number 2, right? Because we're pulling off a second electron. Okay. So this is called the second ionization energy. Now, the energy change associated with that is going to be a bigger positive value. Okay. Bigger than ionization energy number 1. Ionization energy number 2 is going to be bigger than ionization energy number 1. Why is that? Well, it's going to be harder to remove an electron from a positively charged species, right? Initially, we were taking an electron we were taking an electron away from a neutral atom, right? But now we're taking an electron away from a positively charged ion. That's going to definitely be harder to do, right? Because the electron is attracted to that positive charge. It doesn't want to leave. So it's going to require more energy to pull it off. Okay, so thus more energy is required. Okay. And you might be thinking, what about the third, fourth, fifth ionization energies? Well, each successive ionization energy requires more energy than the previous ionization energy. Okay. Now, before we get into more about that, let's discuss the trend in the first ionization energy number 1. Okay. We'll see how that looks on the periodic table. Okay, so the question is, what's the trend on the periodic table as far as ionization energy goes? Well, it's going to increase up and to the right. Okay. So one thing you should notice is that this is the opposite of the atomic size or atomic radius trend, which we talked about in the previous video. What does that mean? Well, it means that it's harder. Oops. Harg. That's hilarious. It's harder to remove an electron from a smaller atom, right? So remember, atomic radius increases down and to the left, right? Ionization energy increases up and to the right, so that's opposite in both ways. So it increases going up this way, right? And it also increases going across this way. So we have the atoms with the elements with the highest ionization energy will be up and to the right, whereas the atomic radius, the largest, would be the bottom left, smallest up top. So it's harder to remove an electron from a smaller atom. Well, why is that? Well, when an atom is smaller, its electrons are closer to the positively charged nucleus. And therefore, the force between the nucleus and the electrons is greater, because the electrostatic force is inversely related to the distance between the charges. So if the electrons are closer to the positively charged nucleus, then it's going to be harder to rip them off. So if you have a smaller atom, the ionization energy will be higher. Okay. So in short, when you're thinking about going down a group, the atomic size increases, right? The electrons are farther away from the nucleus, right? As you go down a group, atom size is bigger. The electrons are farther away from the nucleus. So in that case, the electrons are easier to remove. So if they're easier to remove, then the ionization energy is lower, right? So that's why the lowest ones are down to the left. Okay. Now across a period to the right, the atomic size decreases, right, due to the increase in effective nuclear charge that we talked about in the previous video. So if the atomic size decreases, that means the electrons are closer to the nucleus, which means they're more attracted, and thus the electrons will be harder to remove. So if they're harder to remove, that means there's a higher ionization energy, and that's what we have at the top right. Okay. However, there are exceptions. Okay. There are exceptions. So this problem asks us to explain the following. So basically asking us, why does the trend break here? Notice that if you have a periodic table, it might be useful to look at. But if you look at the top right of the periodic table, we've got boron, carbon, nitrogen, oxygen, fluorine, and neon in the second row. Okay. So we notice here that as we pay attention to the trend, going from here to here, increasing, here to here, increasing, here to here, it's kind of weird, it decreases, but here to here, it increases, here to here, it increases. So generally, it increases, but there is an exception. We talked about this in the intro about how this is just a trend, right? This is not an end-all be-all sort of thing. Okay. So the question is, why is this trend broken here? Okay. To answer that question, we should think about the electron configuration and the orbital diagrams. Okay. So for nitrogen, the electron configuration is the outer electron configuration is 2s2, 2p3, right? Because it has the 1s2 from helium first, but the 2s2, 2p3. So that would be like this: 2s2, 2p3. Okay. So it is half filled like this. Let's do this in pink. So it's half filled, which is pretty stable, right? Because all of these electrons are in separate orbitals. They're all spinning in the same direction, far away from each other. Okay. Now, if we have the ionization energy reaction sort of occur, we rip off one of these electrons, and we form the cation N+, then we have a new electron configuration. We have 2s2, 2p2, right? So we're going to get rid of basically this electron right here. So we're going to have just 2s2, 2p2, okay? So here we ruined the half-filled stable nature, okay? So we lost the stability of having a half-filled orbitals. Okay, so that's not something that wants to happen, right? You don't want to lose that stability. Now, if we think about oxygen's electron configuration is 2s2, 2p4 after that helium, right? The core electrons. So we've got 2s2, 2p1, 2. Let me move that a little bit closer to the right. 1, 2, 3, 4. And if we rip off an electron, we're going to rip off this one, right? Oops. That is not the one that I wanted to do. This one right here. I'm going to take that off. Okay. So the O+ ion would be helium 2s2, 2p3. That's the configuration that nitrogen has when it's half filled, right? So here, this is half filled and stable. And here, it's not that this isn't stable, but this is not ideal, having two electrons in the same orbital, right? That's not as stable as having them half filled, okay? Now, what we see here, basically the idea is that with nitrogen, ruining that stability of it being half filled is going to require a lot more energy than it is going to rip off the electron for oxygen, because oxygen taking off this electron right here actually results in a somewhat stable configuration with these orbitals being half filled. Okay, so that is the reason for this trend breaking here, right? Nitrogen, its ionization energy, its first ionization energy is going to be higher than that of oxygen for this reason. Okay, so keep that in mind when you come across potential exceptions later in your studies, rather. Okay, so we mentioned successive ionization energies being higher earlier, right? So ionization energy number 1 is going to be less than ionization energy number 2, which is less than ionization energy number 3. So as you go further and further, each successive ionization energy is higher. So the question is, why is that? Well, pulling an electron from a more positively charged species is going to be harder, right? Because those negatively charged electrons are attracted to those positive charges. The more positive the charge is, the more attracted the electron is to it. Okay, so we've already shown what ionization energy 1 and 2 look like, right? Well, ionization energy 3, what would that look like? Well, we would just have to take off another electron from whatever just resulted from the ionization energy 2 reaction. So ionization energy 2, we had the X2+ ion. So that's what we'll start with in ionization energy 3, right? And we'll rip off an electron, and that'll result in the X3+ ion. Okay, and then if we want the ionization energy 4, that'll be X3+, taking off an electron to result in the X4+. A simple way to remember it is that if you want to know what the reaction looks like, which is actually really, really useful, it's to just keep in mind that ionization energy number 1 will result in a +1 ion. Ionization energy number 2 will result in a +2 ion. Ionization energy 3 will result in a +3 ion, so on and so forth. Okay. All right. Now, sometimes there are large jumps in energy from one ionization energy to the next. Okay. So I just write that here as ionization energy N to ionization energy N+1. So from one to the next, sometimes the jump in the requirement for energy is pretty big. So that's something to pay attention to. And I have an example of a problem where that sort of situation is involved. So here it says a period 2 element has the following ionization energies. So they give you this little table. So you have ionization energy 1 through 5. And we can see that these approximate values in kilojoules per mole. The first one is 801. Then we go to 2,427. Then to 3,660. And then a huge jump from the 3,000 to 25,000. And then the next one to the 32,000. So we're paying attention to this jump here. Okay, this jump from here to here. That's pretty weird. Okay. The question is, given this information, which element is this and why? Right? It's a period 2 element. Okay. So which element is this and why? Well, if that fourth ionization energy is where it becomes really high, that must mean that the ionization energy 4 reaction is not trying to happen. This is not trying to happen at all. So, if we think about it, this reaction, right, is not going to happen. Right? It doesn't want to happen, at least. So that must mean that this ion does not want to give an electron. It especially does not want to give another electron up. So this must mean this is pretty stable. It must mean it's super stable. Okay? Because if it requires that much more energy, right? Things are super stable when they have filled outer shells of electrons. Okay? It must have a filled outer shell of electrons. Basically, it probably has a noble gas configuration. So the question is now, which row 2 element loses 3 electrons to have a noble gas configuration, right? You can also ask that question of which row 2 element has 3 outer shell electrons, right? And its configuration would be helium 2s2 2p1. If we look on the periodic table, we'll find that that's boron, right? So boron's orbital diagram would be 2s2 2p1. And if it lost 3 electrons, it would lose all 3 of those, and it would have just helium's configuration. It would be B3 plus, and it would just have the 1s2, right? So that means that this B3 plus is representative of this X3 plus. B3 plus, if it had to lose an electron, would become B4 plus, and then that electron would leave, right? But that would mean that this electron here, this electron, would have to come from the 1s orbital, right? So you'd be ruining the 1s2 configuration, that is helium's configuration, which is a noble gas configuration. And that is super stable, and you would not want to this ion would not want to have that electron ripped off. That would be, it would require tons and tons of energy. Hence, the ionization energy number 4 for this reaction here is super high, right? It equals that 25,026 kilojoules per mole, right? It requires that same amount of energy because it would require that amount of energy to ruin this perfect configuration, okay? So which row 2 element loses 3 electrons to have a noble gas configuration? Well, it's boron, right? Because if it loses 3 electrons, it has this noble gas configuration, it doesn't want to lose it. It doesn't want to lose another one, and that's why this 4th ionization energy is so high relative to the 3rd ionization energy before it. I hope that video was helpful. Thank you for watching. If you found that video helpful, don't forget to like, comment, subscribe, and share with friends. Thank you and happy studying.